Hi, this is Dr. Justin Esarey, and this week we're going to talk about neural networks and their uses in social scientific and political science quantitative research. Neural networks come from a certain tradition of research on the neuron, appropriately. In particular, they come from a rather basic mathematical model of the neuron. That, according to at least the sources that I consulted for this class, the Bishop machine learning book and so on, it's not a particularly accurate model of the biological neuron, but nevertheless it's a sort of a simplified form of the neuron. And it's a bit hard to directly link the neural network model through substantive motivation to the uses that we'll put this neural network model to. For example, we can often use the neural network model for nonlinear prediction, or to say this a little more clearly, prediction of phenomena that have nonlinear relationships with observable covariates. We might use this for classification, both retrospective and prospective. So, for example, we might want to classify war cases and non-war cases differently in historical data and then try to predict future classifications based on things we observe about the world. Neural networks can also be used for feature extraction in a manner similar to principal components analysis and factor analysis. And in fact, the neural network model is, in some instantiations, mathematically identical to the principal components model. And a more complicated neural network could even give us a nonlinear version of that model. There are also sort of non-social sciencey uses for neural networks like data compression and various forms of image processing, including denoising and image recognition. The last two of these things here we don't think about too much in political science, but neural networks are used for these. But it's a little bit hard to motivate the model in terms of a substantive connection to any of these uses. You can sort of guess that from the fact that there are so many uses that it would be slightly hard to knit them all together in some kind of overarching substantive framework. It just happens that the neural network model is particularly useful for all these purposes. So to motivate the neural network model, I'm just going to sort of start off by saying what it is and describing how it's fitted, and then show you some examples of how it works and that will hopefully get you interested in using it. So as I said, the neural network model is based on a relatively simple mathematical model of the biological neuron, and the simplest version of the neural network is the perceptron, which was developed in the middle of the 20th century. The perceptron takes a set of inputs. These are input nodes here. And the input nodes are analogous to independent variables in a normal sort of GLM or other kind of regression analysis. And it links each of these input nodes to an output neuron, which then produces an output. So, for example, each of these input nodes will be connected to a neuron, like so. And these connections are one way. A little bit of crowding here. We can label these neurons, say T1 and T2. And then each one of those neurons, and these are output neurons, produces an observable output. So these are like our dependent variables. So to put this in form that a traditional social scientist methodology person might recognize, here are your DVs, and then here are your IVs. you can see we might have more than one dependent variable. We almost certainly will have more than one independent variable. And these neurons are the connector between the two. Now, each output neuron, each of these T1 and T2 neurons, has what's called an activation level. And the activation level, I'm going to annotate this AIK, is a function of the weighted sum, j in 1 to cap j, of the inputs. Okay, so just to make some notational remarks here, I it indexes observations, j indexes input nodes, k indexes output neurons. There are cap j many input nodes. Anything I missed? Oh, and g is the activation function. So AIK is the state, the activation state, of neuron K for observation I. So going back to this network, what we can do is fill in a weight that connects each input node to each output neuron. So this would be like weight 1, 1. This would be like weight 2, 1. This would be like weight 3, 1, and this would be like weight 4, 1. Then there'd be like that arrow there would be weight 1, 2, and so on. I won't fill in, clutter all that diagram out with all these weights, but that's where they are. And so the state of the neuron T1 is just the weighted sum of all the inputs to T1 passed through this activation function. The activation function can be different. There's no canonical choice for the activation function. The typical activation function for the classical perceptron is to say that G of A is a threshold. It's either 1 or 0. And so you might say it's 1 if A is bigger than 0, bigger than or equal to 0, and 0 if A is less than 0, something like that. But that's not the only possible choice. Incidentally, just if I was going to graph this out, it would look a little something like this. Here's the A is the weighted sum. Here's the activation level, and there's going to be some threshold. And as A gets bigger and passes the threshold, which in this case is 0, we go from having 0 activation all the way up to, whoops, didn't draw that quite right, all the way up to 1. So that's your basic, S-step activation function. But there are others. We could have this one, for example. That's a linear activation. So if we draw that one out, it's going to look a little something like this. G of A, 45 degrees, something like that. This is a step or threshold activation. This is a linear activation. And another common choice is the logistic activation. G of A equals 1 over 1 plus exp negative A. And of course, in this case, we have an S-shaped or sigmoid activation like that. It goes between 0 and 1. So those are some various activation functions we might choose. And the last thing to note is that the perceptron is going to choose, we are going to, the computer program, or we, the analyst, are going to choose weights for the perceptron in some way, because obviously those don't come from nowhere. And the perceptron is designed chooses weights W to minimize the sum of squared errors of the output predictions. So something like this. I equals 1 to cap n, y, I, k. That's the observable output minus t, I, k squared. And here, what we're doing is we're using t, I, k is equal to the activation level of I, k. So I'm just using the name of the node as opposed to the activation level to annotate that. This would be appropriate for if we only had one output. If there were more than one output, we would have to account for that. And so what we would do is we would sum over all the total number of outputs. 1 to n y I k minus t I k squared. Something like that for more than one output. So this whole framework might seem very familiar to you. To put it another way, what's a model where you take a bunch of independent variables, you multiply them by some weights, you add them up, and you get a prediction for a dependent variable, and your weights are chosen to minimize the sum of squared errors? Well, that's regression, right? It's worth noting that the single layer perceptron with a linear activation is very similar to regression. If we do a logistic activation, it should be very similar to a logit model fitted via nonlinear least squares. These single layer perceptron models may not initially appear to be super exciting because, you know, who cares? We could just run a regression, we could do a logistic regression. And if this was as far as the neural network models actually went, I'd probably agree with that. I'd probably say this is a waste of time. But the neural network models, fortunately, I suppose for us, do get a lot more complicated. And the fruit of that complication is that they are able to do things, to model nonlinear relationships that regression and logit can only model with some difficulty. So I'm going to use the single layer perceptron to motivate an algorithm for learning the weights that go into this neural network, with the understanding that we probably wouldn't ever really do that. We wouldn't use a single layer perceptron very often because we could get the same idea, the same results out of a much more familiar and simpler model. But then that learning algorithm will come in very handy when we propose a more complicated model that will do much more interesting and complicated things for an analyst. So with that in mind, let's talk about how these models can be fitted, these single layer models can be fitted to data. So for a basic single layer perceptron, we actually could use the sum of squared errors optimization techniques that we use on regression or a nonlinear least squares logit or whatever. But neural networks have their own updating algorithms, their own learning algorithms that are designed specifically for neural networks and are especially helpful when we get to more complicated networks like the MLP, the multi-layer perceptron. However, these algorithms are still rooted in the same error and minimization ideas upon which algorithms like Newton-Raphson are built. So I want to consider a particular weight. This is a vector of weights, a j by 1 vector of weights. And we're going to suppose that we're going to update this, this vector of weights iteratively. So repeatedly updating it, learning with each iteration, getting better weights and better weights each time. And if we repeat this iteration, if we're on iteration number r, so r is current iteration, the next iteration's vector of weights is going to be some function of the current iteration's vector of weights. This is also j by 1. But we're going to change it, obviously. And we're going to change it according to eta, which just forget about that for a second. We're going to change it according to how much the sum of squared errors, e, the error function, changes as a function of our current vector of weights. So this delta EWR thing is the gradient of the error function with respect to the vector of weights r. What's a gradient? Well, a gradient is just a mathematical function that collects information about the total change in some function as a factor of all the arguments to that function. So in this particular case, if we have one output y, we would write that the gradient is a column vector of derivatives of the error with respect to each weight argument. If there were more than one output, if cap m was, say, 2 or 3, we would have multiple columns that would correspond to each of the derivatives of error with respect to weight for each output, and correspondingly these weights would have multiple columns because there would be multiple sets of weights corresponding to each output. So what we're doing is we're saying we're going to start with our whatever our weights are, and we're going to change them in a way that tends to make the error smaller. So we're going to look at the gradient of the error function. In other words, we're going to say, which direction do we go in order to make e smaller? And we're going to go in that direction. We're going to move in that direction with respect to w. So the only additional factor here is this eta thing. This eta is just a scalar, 1 by 1, learning rate. And typically, this is between 0 and 1. Oops. Doesn't necessarily have to be, I suppose. You could set it outside those boundaries, but if you set it too large, the algorithm's going to fly all over the place, and if you set it too small, the algorithm's not going to move. I wouldn't set it less than 0, though, because then you'd be going in the direction opposite of the good direction, of the error improving direction. So I think 0, and it shouldn't be 0 because then you don't move. So I think 0 is a realistic lower bound. Anyway, that's all there is to it. That's the way the Perceptron's learning rule works. Just change the weights in a direction that tends to make the errors smaller. Now, of course, we can draw out the implications of this rule a bit that make it possible for us to implement it in code. So for the perceptron, the error function is just EW equals sum of I in 1 to cap n, n being the number of observations, y minus I k, whoops, sorry, yik, k being the output. In this case, we're primarily talking about there being only one output, so really this would just be yi, minus g of sum of j in 1 to cap j, w, j, k, x, I, j, entire quantity squared, times a half. And we're going to put this half out here without loss of generality. Minimizing half of something is the same thing as minimizing something. This is just a scaling factor that's going to make what we do next a little bit more convenient. Noting this is just the activation level of node K. So if we only have one output, we don't really need the K. We can just say yi minus ti. But in the case that we might have more than one output, we'll keep the K in there just to make it clear how this derivation would relate to that multiple output case. So you can see from our updating rule that we need the derivative of the error function with respect to each weight. And so we can just pick an arbitrary weight to take derivatives. They'll all be of the same form, wjk. And what we're going to have here is negative. So we're going to use the chain rule twice. We're going to take the derivative of this function with respect to its argument, then the derivative of this function with respect to its argument, and then the derivative of this function with respect to its argument. The negative appears out front because this g bit that has the w in it is itself negative. So what we have here is the sum of I in 1 to n times yik minus g of the sum j in 1 to cap j. There we go. wjk xij. Now it's not squared anymore because this 2 comes out front, which this is why we put the scaling factor there, so it cancels out to 1. We get this to the 1 power. Then we need to take derivatives of this function, dg d its argument, a, which is everything on the inside. And then we need to take the derivative of this argument with respect to the weight, which gets us to the final derivative that we're interested in. So if we use a very simple linear activation function, which gives us that dg dA is 1. G of A is A. dg dA is 1. Then we can rewrite this as dEw dwjk equals negative sum I in 1 to cap n yik minus tik times xij, where this guy is this guy. So if you need it written out for you, A is the sum of wjk xij, sum being over I, the number of observations, dA dw jk is just xij for that particular, for each I, so the sum of xij. But since the sum's already out front, we're only taking this derivative with respect to, with a single observation in mind, as it were. And so this little derivation can get us to the final perceptron updating rule that we would use if we were programming the perceptron, the single layer perceptron, which is each weight should be updated. Oops. Here we go. Each weight should be updated by taking the existing weight value and adding eta. Now, it was subtracting, but now we're adding it because this quantity is negative. We're going to subtract eta times negative this. So we're adding eta times this, which is quantity, sum I in 1 to n, yik minus tik times xij. And then you would do this for each row of weights. So if we only have one output, we don't need to worry about that last bit. K is just 1. So we're just updating all the possible weights in the model. And some algorithms actually randomize the order in which this weight updating happens. But some algorithms also just do it in sequence. Start with the first weight, move on to the second weight, move on to the third weight, and so on. So that's it for a basic for a basic perceptron with a linear activation function. You're just updating each weight a bunch of times by adding some function of the error times a learning rate eta. The existence of a more complicated linear or a more complicated activation function changes only one bit. Oops. The nonlinear activation function is just going to make this something other than 1. So what happens if, for example, we have a logistic activation function? Well, the only part that's going to change is dg a dA. Now, g of a is 1 divided by 1 plus exp negative a. So the derivative of that with respect to a, using the chain rule again, is, now remember, we could write this like this. It's p-a, whoops. Let me write it down here. 1 plus exp negative a, negative a to the negative 1. It's the same function. So I can write this as negative 1 times 1 plus 1, or 1 divided by 1 plus exp negative a squared times the derivative of this with respect to a, which is negative 1 times exp negative a, the end. That's what we have, applying the chain rule twice. So I can actually rewrite this a little bit. We're going to have these negatives that are going to cancel out. Might as well just get rid of those. So we can rewrite this as exp negative a divided by 1 plus exp to the negative a times times 1 over 1 plus exp to the negative a. I hope you'll see that's exactly the same thing. I've just rewritten it a little bit. And the second part you'll immediately recognize as g of a. This is actually 1 minus g of a. And I'll leave that as an exercise to the listener, but you can very quickly show that that's true. If you subtract 1 minus g of a and sort of just do the algebra, you get this expression. So what that means is all we need to do to change our learning rule to account for the nonlinear activation is just add that bit into this expression. So if I take this, I just sort of copy that and then move it down here. Let's drag it over here. Okay. So now I want to add in that dGdA into the derivative that I need to have in that expression. So all I need to do is just add in to this expression 1 minus g of a, which is the activation, the sum of w, j, k, xij, the sum being over j, times g of the same thing, wjkxij. And then the rest of it is the same as before, times xij. And now we have the updating rule for the logistic. Which looks a lot like the updating rule for the linear model, but, you know, just with that added logistic activation function in the middle. So that's how the updating rule works. And again, not that impressive for a single layer perceptron because there are actually easier ways to do it. But now what I want to do is talk about some limitations of the single layer perceptron, how the multi-layer perceptron goes beyond those limitations, and then take this algorithm we just developed and apply it to the multi-layer perceptron. So as I mentioned, the perceptron was developed in the middle of the 20th century, and research on it stopped for a long time because some computer scientists pointed out that it has some important and it was thought to be damning limitations. One of those limitations is that a single layer perceptron cannot approximate the XOR function, exclusive OR. Now remember that the perceptron was developed as part of a line of research that was ultimately rooted in cognition and brain science. And the inability of this model to approximate a relatively simple cognitive action that's, for example, part of logic and computer systems was thought to be a really big problem. So if you take a look at two variables, x and z, and we'll say that there's a dependent variable y that has two classes, yes and no, on and off, 1 or 0, some kind of binary classification. And we'll say that x and z also have only two categories, 1 and 0. The exclusive OR function says that if either of its inputs is 1, then the output is 1, but not if neither are 1 and not if both are 1. So you can imagine this being like, there being, let me write this in another color here, being like a 0 here, and a 0 here, and a 1 there, and a 1 there. Now, is there any linear way, remembering that the perceptron is linear, of dividing this xz space in a way to put all the 1s on one side and all the 0s on another? Well, the answer is no, there isn't. Now, if we could do something non-linearly, we could solve this problem quite easily. Now we put all the 0s on one side and all the 1s on the other. You could do it, and actually there are multiple ways of doing it. I could have done it this way as well, right? Another somewhat tricky way of doing it is to add a third dimension, which is can even be an irrelevant dimension, something like here's x and z, and now here's w. So we've got x here and z there and w. And just like before, we've got 1, 0, 1, 0. And now w, we can also make a binary variable just for clarity. And what we'll do is we'll make the 1s out here, we'll put them out on w equals 1. This is 1 and 0. So we'll say that the 1s are x, 1, 0, and, or they're at 1, 0, and 0, 1 in xz space. So here's 0, 0 in x space, 1 in z space. We'll put that floating out here. And then 0 in z space, 1 in x space, we'll put that floating out here. So these are both observations are both on the plane defined by w equals 1. There's x equals 1 right there. So I'm going to actually circle these so that you know that they're observations. And then the 0s we're going to leave in the plane where w is 0. So that's the 0, 0 observation and the 1, 1 observation, or up here. So now it would be fairly easy for me to divide the 0s and 1s with a linear function. I could do it with a simple, I could do it with a plane. Now let's see if I can actually draw this. It's going to be a little hard to draw. But imagine I put a line here at w equals a half. And then I just extend that plane up like this. So that you imagine putting a fence sort of down the middle of the w-axis. So the zeros are on one side and the ones are on the other side. What I've done here is effectively to introduce an interaction variable. And so I've said that when w is 1, sort of that's the relationship. And when w is 0, that's the relationship, something like that. It's not quite that because we actually don't have w, or we don't have y in this space. And so I would need to put z, x, and y in a three-dimensional space and sort of show you how the functions would differ. But conceptually, it's effectively the same thing as saying introduce an interaction variable, and I can split these functions quite easily. So maybe I can do this with some tricky thinking in a linear model. Or maybe I could propose a nonlinear function to do this. Proposing a nonlinear function is pretty much exactly what a multi-layer perceptron is, what it does. Imagine taking the inputs like before, and I'm going to just have 4 inputs for demonstration. And I'm going to just go down to 1 output. So here's my inputs. Here's my outputs. If this were a single layer perceptron, I would just link the two. But what I'm going to do instead is I'm going to introduce another layer of nodes, H1, H2, H3. This is called the hidden layer. Each one of the outputs is going to be linked. I said that wrong. Each one of the inputs is going to be linked to each hidden node, like that. And then each hidden node is linked to the output. That's a multi-layer perceptron. And I should note, this is called the hidden layer. So this is a single hidden layer, multi-layer perceptron. The activations of each node are still a weighted sum of the inputs, just like before. The only difference is that this last node, T1, now is taking the hidden layer as inputs, as opposed to taking the independent variables directly as inputs. So the activation of a hidden layer node, for example, the activation of some node HK for observation I, is just the activation function of the sum of all its inputs, just like before. Looks pretty similar. But now the activation of the output node, and we've only got one, so I'm just going to denote this Ti, is the sum of all of the activations of the hidden nodes that lead to it. So I've added V here to indicate that the weights connecting inputs to hidden layers are denoted with W, and then the weights connecting the hidden layer to the output are denoted by V. So VKM is the weight from HK to TM. And because we only have an M of 1 in this case, we can just, well, I'll keep the M's in there just for there we go. So M is the number of outputs. But in this case, we only have 1 output, so M is just going to be 1. And we can omit that index. Right, so that's it. That's all there is to it. Now, what have we done? What is this network actually doing? Well, if you think about it, if I were to consider just this portion of the network, now I've omitted the actual output here, so here this actually leads to some dependent variable. If I were to link this hidden layer node directly to the output like that, and not have this output node. This is actually an output. I should write this. This is not an output itself. It's an output node or neuron. And then this is the actual output. If I were to take this hidden layer node, H1, and connect it straight to the output, I would have a single layer perceptron. Inputs, output node, or output neuron, connected to output. And in fact, each one of these hidden layer nodes I could do the same thing with. So I have a second single layer perceptron right here. Whoops. If I were to connect this one to the output, I'd have another single layer perceptron. And more importantly, the weights that connect the inputs to this hidden node are not necessarily, and generally are not, the same weights that connect the inputs to this hidden node. So in short, what I actually have here is multiple, I've got multiple single layer perceptrons that I'm knitting together. So if I take a space here, like this, I can imagine single layer perceptrons. Here's a single output and a single input. I can imagine each single layer perceptron being a line in this space, right? It's a fitted linear function, the same as I would get in a linear regression. This, of course, assumes a linear activation. But I've got more than one of these single layer perceptrons. I might have another line that looks like this, and I might have another line that looks like this. Maybe not like that. That's not that interesting. Maybe like this. And so what the single layer perceptron is doing, is just fitting a line. What the multi-layer perceptron is doing is taking all of those different outputs, multiplying them by weights, and adding them up. So each point x, the multi-layer perceptron will take all of these weights, compute some kind of weighted average, and then plot a point on that line. And then as we move through x, we're continually computing weighted averages of all these different points. So the resulting function can actually be nonlinear. We can take, let me just say that again, we can take a series of linear relationships in a perceptron, in a single layer perceptron, and combine them in a way that actually makes the result nonlinear. And you know, I'm not really sure, whoops, I'm not sure exactly what this would look like as a nonlinear function. So you can imagine at this point we'd have a point that's sort of biased upward toward here. At this point these two are going down, so it's going to look something like that. Here we've got two closer to the bottom, so it's going to be, yeah, somewhere like that. This is going up faster, so it's going to be hard to say exactly what this is going to look like. I'm not sure. But things can get even more interesting if the activation functions are not linear, but are logistic. So again, consider we've got multiple single layer logistic perceptrons. And we're taking a combination of them to compute, oops, the point on the multi-layer perceptron at each point. So we might get something nonlinear out of the combination of these S-shaped functions. And the Bishop book has some nice illustrations of what this combination might look like. So, to summarize, a multi-layer perceptron is a way of knitting together multiple functions which are individually not that complicated and combining them via weighted linear sums to produce an output neuron or an output activation that's substantially more nonlinear and more complicated than the sum of its components, the sum of its parts, rather. I should also note that it is not only possible, but not terribly uncommon to have more than one layer of hidden neurons. So, we could, for example, propose this network that has two hidden layers, of neurons. And what this network would do is take a combination of single-layer perceptrons at each of its second hidden layer nodes, and then combine those nonlinear functions to an even more nonlinear function for the output. So in other words, imagine taking these black lines, making multiple versions of them, and then combining them via weighted sum to create an even more nonlinear function. That's a possible thing to do with the neural network, with a neural network model. So the idea is you can, by increasing the number of nodes in the hidden layer and increasing the number of hidden layers, you can increase the nonlinear complexity of the network to whatever level is appropriate for your particular application. In other words, this is a sort of general purpose nonlinear model that can be made it can be made complicated enough to tackle any nonlinear modeling problem that you might have. Now let's take a look at what these neural network models can do in application. So what I've done here for this example is I've created a relatively complicated relationship between x, z, and y. In particular, y, the dependent variable, the output in our neural network framework, is a combination of a sine function around x and a cosine function around z. So that if we plot y against x, you see this sort of curvilinear, highly nonlinear function. And the same thing happens in z space. And these waves are sort of, they don't peak at the same time in x and z space, so the resulting function in y is very nonlinear. Trying to estimate a generalized linear model in such a case would be extremely annoying, because not only would you have you would have nonlinearities in the x dimension and in the z dimension to take care of. You might guess that a sine function might work, you might not. And we're not even accounting for the possibility, which doesn't exist in this example but could easily exist in real life, about cross nonlinearities between x and z. In other words, as complicated as this example is, it could be even more complicated, and in that case, GLM is going to be really, really hard to deal with. So instead of trying to do that, what I'm going to do is try to estimate a neural network instead. And so let me just start this running and then talk about what I've done as this runs. Oh, I've got to create the data set. Here we go. So I'm using the neuralnet library, neuralnet function in order to do this. I run the neuralnet model with the appropriately named neuralnet label. I give it a formula of the relationship I'm looking to model, y as a function of x and z. I give it the data set, and I tell it I want a single layer perceptron with 4 hidden nodes. That's what this model does. Step max is the maximum number of iterations that it will run through in order to calculate this model. And we haven't talked about exactly how this works yet, but it's a variation on the learning algorithm that we just talked about. It's called error backpropagation. And we'll talk a little bit more about the theoretical how this procedure is implemented in just a second. But suffice to say that it's related to this weighted updating rule that we just talked about for the single layer perceptron. The threshold is the point at which we've decided that the model has converged. In other words, how big does the difference between the weights have to be, or how small does it have to be before we've decided we're not getting any better and we can just call the model converged. And this life sign function is just going to tell us, it's going to create these little updates to tell us that our neural network is actually sort of updating, and how it's how the error is changing over time. And actually, I believe the threshold is the derivative of the error, not the total error. When we're done and we use plot NN, we get a picture of the network we just fitted. Here's our two inputs, X and Z. These are connected to the hidden layers via these weighted functions here. And then here's the output node Y, and that produces the prediction that we observe Y hat. Now you'll notice that X and Z are two nodes, but it also creates these one nodes. These are analogous to the constants in a linear regression. So in a single layer perceptron, the one node is just a constant. And what you do is you add a constant at each level or each layer of nodes. So for example, I've got a constant at the output node here, but I've also got a constant inside of the hidden layer nodes. And the neural network package will compute this, will add that bias node automatically. So are the predictions of this neural network any good? Well, in order to figure that out, what I can do is use the compute function. So the compute function runs a bunch of inputs through this neural network that's been trained, and then computes the predictions for Y that result from the data we run through. So what I'm going to do is I'm going to run through this matrix of data. You can see the first column is X and the second column is Z. And what I'm doing is I'm just running through a bunch of values of X, holding Z constant at 1/2, and I'm going to see what predictions I get out of that, and then I'm going to plot those predictions against the actual observed Y values. And in the X dimension, this network is actually doing extremely well. You can see this line here is really following really well. And actually, I think to make this look better, I'll change that line to be red. Can you see that? Maybe I'll thicken it a little bit. LWD equals 2. There you go. So now you can see that prediction is actually quite good. But if I do the same thing in Z, I'm going to add this here. So now I'm just looking at the Z space. Oh, this network's not fitting very well at all. It's putting a straight line through 0 through a very complicated space. So this is not good. We need to make this model more complicated. It's fitting X really well, not fitting Z at all. So what I'm going to do is I'm going to just repeat the thing I did, but I'm going to add 4 more nodes to the hidden layer. So this is going to allow there to be a greater number of what we talked about as being single layer perceptrons that are all operating in concert. And I'm going to add them all together to form the total output of the neural network function. And adding more of those hidden nodes allows the network to model a more complicated nonlinear surface. Now, it's pretty common for these neural networks to take a long time to fit, especially if you've given it a rather complicated problem and you're giving it a lot of flexibility to decide exactly what space to fit. It's got a lot of weights to fit. So this can take a while. So what I'm going to do is I'm going to pause the video as this updates, and then we'll start again once it's converged. Okay, so now we have a more complicated network, and you can see there's 8 nodes in the middle that we fitted. And what I'm going to do is just do the same thing. Look at the predictions in X and Z space. I'm going to make the lines thicker and redder like I did before. So, looking at the predictions in X space, still good. That's good to hear. And what about Z space? Looking good. Still good to see. So, a more complicated network was able to fit this space. So, what are neural networks good for? Well, they're good for solving these complicated complicated modeling problems where the space may or may not be known. We may not be able to know, we didn't know well enough to fit a parametric space to it. The neural network will sort of decide on its own using this organic procedure that we described to fit the space that minimizes the sum of squared errors. And it sort of does this on its own. We just tell it the number of nodes in each layer, and it decides how to knit all those functions together to give us the best prediction possible. Let me give you another example of a problem for which neural networks are well suited. Neural networks are well suited. So Here's a little classification problem where what I've done is I've proposed two classes, 1 and 0. In this plot, they're sort of square and circle. And what happens is that the class of the observation is determined by whether the observation lies in a circle with radius 1/2 to the square root of a half, which is about 0.7. In the xz space. So imagine drawing a circle here with radius of about 0.7. If the observation lies inside that circle, it's class 0, and if it lies outside that circle, it's class 1. But there is some noise. You can see that there are some circles in the square space, there are some squares in the circle space. So it's a noisy classification problem. Now imagine trying to classify circle and square space. To figure out what the best dividing line between those spaces is in the XZ subspace using a logit or probit. So what I've done is I've run a model predicting y, which remember is a 0, 1, using a binomial GLM, probit with probit link. And then I'm going to predict the response type based on whether the predicted probability is greater than or less than a half. So if it's greater than half, I'm going to classify it as being a 1. And if it's less than a half, I'm going to classify it as being a 0. And I'm going to color the 1s red, and I'm going to color the 0s blue. And then I'm going to redo this plot, but I'm going to color the observations according to how they were classified by the GLM. And what do we see? Well, what we see is that circle, there's the boundary of the true classification space. What the linear model did, or I'm sorry, what the GLM model did was draw a line right through that circle, and it kind of snipped off the corners and it said, that's the best I can do. I'm going to classify some of this blue space, or some of this red space is blue, and some of this blue space in here is red, but there's nothing else I can do about it because I can't draw a circular line. Now, I could maybe get a circular line if I added a bunch of polynomial terms to my GLM, if I was presuming I was smart enough to do that and knew enough about the data set to be able to propose a correct parametric function. Or, alternatively, if I didn't know what to do, I could run a neural network analysis on this data and let it classify the data for me. So what I've done is I've specified the linear output is false. That's telling the neural network algorithm that y is a binary classification. And so you should use a logistic activation function in both the hidden layer and in the output layer of the network. Just so you know, neural networks don't necessarily have to have the same activation function in all their layers if it's a multiple layer perceptron. And in fact, the model we just fit in this X and Z problem, it had a logistic activation in the first layer and a linear activation in the second layer. So that's very common when the dependent variable is continuous. But in this case, the dependent variable is binary. And so we want a logistic activation in both layers. All right, so it's run. We've run it with just 4 hidden nodes. How well do we do? Well, I'm going to compute the prediction for the in-sample data, and I'm going to see how my neural network model does. Well, to be honest with you, it's actually doing a little too well. You'll notice it's classifying the squares as blue even if they lie outside the boundary, which that's noise. It's fitting some noise. And it's classifying the circles as red even if they're inside the boundary. It's, again, fitting some noise. So we might worry about overfitting. Maybe we've actually done a little too well in this case. So what I'm going to do to see if we've overfit the data is I'm going to create test data. So it's very common in classification problems to have test data and training data. So training data is what you use to fit the model, and then test data is data that you hold back from the training model to see if you've done a good job. It's a version of cross-validation, which we've talked about in the past. Now, in this simulation, I don't actually have to hold back any data. I can just create it. I can just say, oh, well, create some new data out of the same BGP. How well does our neural network model classify this new data? Well, it classifies it quite well. You can see that it's basically following that boundary extremely closely. It's putting everything inside the circle into the blue category and everything outside the circle into the red category. And yes, it makes some classification errors, but that's unavoidable because this is a noisy fitting process, and so some degree of misclassification is inevitable. The true DGP is this circle, and it's coloring it in pretty well. The GLM model is not going to do well at all. I actually didn't do it for the out-of-sample data, but it would be just as horrible as it was before. It would just draw the line, and that would do the same thing. So those are some examples of what neural nets can actually do for you in application that are pretty cool. The basic takeaway is if you have a highly nonlinear problem and you don't know enough about that problem in order to write down a parametric model, a neural network might help you uncover those nonlinearities in a robust way if you can spare the computational time and you're willing to toy around a bit with the structure of the model, the right number of nodes and the right number of layers in order to get the right information out of it. All right, so let's talk a little bit about how a person would fit a neural network model, a multi-level perceptron type neural network model. The models are fitted using a process called error backpropagation, which you can see at the top of the page here. An error backpropagation is a relatively simple concept that unfortunately has a relatively complex implementation. So the idea of error backpropagation is that not all of the weights are directly connected to the outputs, and so these weights don't have necessarily a direct effect on error, but they do have an indirect effect. So for example, going back to our original multi-layer perceptron here, this weight W does affect the error in prediction for this T1 output neuron, but it only affects T1 error through its effect on H1. And so the idea of error backpropagation is that we calculate errors at this node and then backpropagate them to the previous nodes to enable us to figure out how much the error changes as a hidden node weight changes. So here's how error backpropagation works. The first thing you do is initialize all the weights, and that can be done with some kind of random number generator. The second thing you do is calculate activation levels in the network using the inputs and the current weights, which in this case we just initialize them so that the initial weights, moving left to right, where left is the input node side and right is the output node side. Okay, now that you have activation levels for the entire network, at each output node, calculate the derivatives needed for the update rule. And those derivatives are, for the VK weights, VKMR equals VKMR plus, or I'm sorry, I inverted these two. It should be R plus 1 equals VKMR minus eta times the derivative of the error function with respect to VKM. Now, we have to figure out what this is. What's this derivative? So we can use the chain rule to figure out what that derivative is. In particular, we can write the derivative of the error function with respect to VKM is equal to the derivative of the error with respect to dGA, where G is the activation function, A is the argument to that activation function, times dGA dA times dA dVKM, remembering that in any perceptron type network, A is just going to be the sum over, is that right? JKXJ. the sum over the inputs and the weights. But of course the trick is we're actually at the output node in MLP, and so we actually aren't directly connected to the outputs anymore. We're directly connected to the hidden layer nodes. So in this case, it's going to be VKM times HK, where H is the activation level of the hidden node for a particular observation. So we know what all of these things are. We know, for example, that this, from our previous example, is just going to be ym minus tm. We know that this is going to be hk, right there. And we know that this is going to depend on the activation. I should say on the activation function. Now, I've written this in a sort of a general way. If we were looking at an individual observation, we could annotate this as, you know, each one having its own individual I here. Which is just to say that we can calculate this derivative, well, how do I put this actually? We can calculate this quantity, this derivative for each observation I, and then sum up from I in 1 to n to get the total change in the error. I guess that's the best way to put it. But I'm writing it in this general function, just omitting the subscripts to save on some notation. So now we've got the what we need to calculate updates at the output nodes, but what we don't have is how to calculate updated weights for the hidden nodes. And we're going to use the chain rule again. And again, we're going to use the same update rule we did before. Oops, JK. But now we need this, and this expansion is going to look similar to the previous expansion, but there are going to be some important differences. So we expand this out via the chain rule to be times equals DEV DAM, where A is the activation level of node M, DAM DWJK. And if we have multiple output nodes, where the output nodes are indexed via that little M subscript, we have to sum up over all those different outputs. So what this is, for example, this right here, is the amount that the error changes when the activation node of output, when the activation level of output node M changes. The idea here, if we go back to a diagram of the perceptron, is that when I want to know how much this weight changes the error function, I have to determine this hidden node's total effect on all the different outputs. In this case, there's only one output, but this could very easily be connected to 2, 3, or 4 different outputs. And so when I change this weight, all of those errors are going to change because this hidden node is going to propagate through to all those different outputs. So this recognizes that I want to look at the amount that the error in my predictions change at each output node as a function of V. As a function of AM, the activation level of output node M. Then what I need to do is figure out how much the activation of that hidden node M, of the output node M, changes as a function of the weight WJK. Now again, we know or can write expressions for both of these things. In particular, this is just going to be DEV DGAM DGAM, DAM, but we just figured that out. Here's the same, this is the same function right here. That, if I can go down here, is going to be the same as this. So we've actually already calculated this in the previous update. So what remains is just to calculate this, and that can be done again using the chain rule. DAM dWJK is equal to DAM dG of maybe AK, dG of AK, DAK, DAK, dWJK. So how much does the activation of the output node change as a result of the activation of the input? How much does the activation of the input change, or of the hidden node? Let's just take that. Let me start again. How much does the activation level of the output node, actually, I should even take that back. How much does the sum of the weights that go into the output node change as a function of the activation level of the hidden node? Now, I'm making a distinction between the index that goes in and the activation level, because the activation level is technically what you get after you pass through the activation function, and this has not been passed through the activation function. So, weighted sum of the hidden node, or of the output node, how does that change with respect to the activation level of the hidden node? How much does the activation level of the hidden node change as a result of its inputs, its weighted inputs? And then how much do its weighted inputs change as a result of a particular weight? And this is going to be, well, that right there is going to be VKM. This is just going to be XJ, and this is going to depend on the activation function. We can actually rewrite this a bit, because if you'll notice, this thing right here that we use again down here in computing the total derivative, we can sort of just call that, give that a name, give that quantity a name, and write DEV dWJK equals the sum from m in 1 to cap m of delta m times VKM times XJ, and that would be for the linear activation, which enables us to get rid of this bit right here. And this DM thing is what we calculated before, DEV DGA DGA DA at the output node. Now, I've written this in such a way that the activation functions are the same at both the hidden node and the output node, and I've done that just for convenience, but just to remind you again, they don't necessarily have to be the same, and in fact, very often, they're not the same. So what that means is we can actually summarize steps 3 and 4. We can sort of break that down or collapse that into a combined process of calculating delta IA equals DEI DAA for all output nodes for observations I. And then calculating DE DWBA, actually this would be for all nodes, not just for all output nodes. For all nodes, I'm sorry, I made a mistake. This would be calculating DE DWB equals delta IA times BI for all weights where, actually I should fill in this as beta alpha, where beta is the activation node for node beta, and delta IA is as above. And WBA, or beta alpha, is the weight connecting node beta to node alpha. And then finally, we can use what we just calculated to conduct all the updates. W beta alpha R plus 1 equals W beta alpha R plus eta times this thing, DE DW BA alpha. There we go. So that's sort of just a compression of steps 3 and 4 into calculating these deltas and then carrying them forward into the, or yeah, I guess carrying them backward into the previous calculations. And then step 5 is just to repeat 2 to 4 until convergence is reached. And convergence is reached where WR plus 1 minus WR is less than some quantity for all the different weights in the network. So, pretty complicated, but the idea, I hope, is fairly simple. We're just carrying forward the idea of gradient search, steepest descent, from the simple single-layer perceptron to the multi-layer perceptron, with the added complication that the layer of hidden nodes, their effects on error have to be backpropagated through this indirect technique. Let me talk about some practical aspects of fitting neural networks in real data, which we've already seen some examples of doing. The first thing, and this is something that's noted in the Bishop textbook, there are no formal ways to choose the number of nodes in a network. I should actually, the number of hidden nodes. There are pretty good ways to choose the number of input nodes. You count the number of inputs. But there are no formal ways to choose the number of hidden nodes in a network or the number of hidden layers. So these largely don't exist. Now, there are things we can do to choose anyway. We can, for example, look at fit characteristics in and out of sample. For the likelihood variance of the neural networks, there are AIC and BIC computations that the neural network package in R will perform for you that you can use to compare networks based on fit and on the number of equivalent parameters that we have in a neural network. But there's no hard and fast procedure or way of deciding how complicated your neural network needs to be. Ultimately, that's a matter of, is it doing a good job of doing the thing you want it to do, which is usually predicting out of sample or in sample. The second is that inputs and outputs should be scaled. Again, not necessarily a hard and fast rule, but it's generally a good idea. Centering variables on 0. And setting the standard deviation of 1 can improve fit performance. And in addition, as we'll see in a second, neural networks, single-layer perceptron neural networks, are equivalent to principal components analysis, and ergo, the same reasons for which you'd want to scale things going into a PCA would also apply to neural networks. Third, there may be multiple local minima in a neural network. What that's a way of saying is, remember that a multi-layer perceptron or a single-layer perceptron is ultimately about minimizing the sum of squared error, choosing W to minimize the sum of squared error. But it's very frequently the case that the objective function for the sum of squared errors looks a little something like this. And it's pretty common for a neural network steepest gradient process to go here and then stop there. And the software packages that exist try to take care of this. They try to address this in various ways. One of them is to fit multiple networks with multiple initialized starting values. That's a way of ensuring that the answer you get is a good answer. Another thing, there are also various algorithmic refinements. Various resilient algorithms. I'm definitely waving my hands at this. I'm just sort of pointing out that there are various tricks that one can apply to an algorithm to try to shake it out of a local minimum and make sure you're not at least too shallow of a local minimum. And then finally, there may be multiple global minima, multiple equivalent global minima. Whoops. Which is a way of saying that there are, a neural network model is over-parameterized. There are lots and lots of things to tweak, things to fit, parameters to choose in a neural network. And I can choose multiple sets of parameters that actually give me the same answer, the same fit characteristics. And so, just because you don't get the exact same pattern of weights in a network doesn't necessarily mean it's not the same network. You really need to look at the fit space, the mapping from the IVs into the DV in order to sort of see whether your solution is really equivalent. So these are things to keep in mind when you actually go to apply neural networks to a live problem. So I'd like to wrap up with one last application of neural networks, linear and nonlinear feature extraction, principal components analysis. I want to start off by talking about what you might call, or what is called in the literature, a single hidden layer auto-associative network. Auto-associative means that the same things go in as come out. So I've got x1, x2, and x3 here. And the outputs are actually the same. Now I'm going to denote them as prime to indicate that they're coming out of the network as fitted quantities, not going in as raw data. We might pass this network through two hidden nodes, Z2 and Z1, and then these hidden nodes then propagate their information through to the outputs. Typically, if this sort of audio-associated network is used, this linkage will be nonlinear, something like the logistic, and this activation function will be linear. Now think about what we've just done. We're using x, y, or x1, x2, and x3 to predict x1, x2, and x3, but we didn't draw this network, for example. We didn't throw in 3 hidden nodes and then use all 3 of those hidden nodes to predict x's. So this would be, all going to the x's again. The reason we didn't do that is because we're actually taking a three-dimensional space and then compressing it down into a two-dimensional space before we then expand back into a three-dimensional space. This sounds a lot like principal components analysis, and in fact, it's equivalent to principal components analysis in this specific case where we're looking at a nonlinear logistic mapping. Actually, the PCA, I believe, is both ends are linear. So if this were truly this equivalent to PCA, this would also be a linear mapping. If you map a 3D space into a 2D space via a linear map, and then take that 2D space and map it back into the 3D space with a linear map, you are literally performing PCA. It can be shown that these are mathematically equivalent to one another, those two procedures. You might get slightly different answers because the PCA neural network version is fitted with a different backpropagation procedure than normal PCA, which is calculated by a singular value decomposition or some other process of finding eigenvalues and eigenvectors. But nevertheless, in the limit, when things are working correctly, they're the same. That's not that interesting because we already have lots of good ways of performing PCA, probably better and easier than neural networks. But it's interesting to note this connection because it allows us to think of what we might do with something like this. Here's a 5-dimensional space. We're mapping that into a 3-dimensional space, then into a 2-dimensional space, then back into a 3, then back into a 5. And I'm not, well, do I really want to draw these lines? There's going to be a ton of lines here. 1, 2, 3, 1, 2, 3, 1. I'm not going to put all the arrowheads on because that would be super annoying. Okay, and then this 2, 2, 2, 3, 3, and then each one of these is going to have 5. 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And these nodes will have a nonlinear activation, usually a logistic activation. And these nodes will have a linear activation. This network that I've just written down allows us to perform what's called nonlinear principal components analysis. Which is just a way of saying we can take a bunch of data, a couple of data vectors that we have, a couple of variables, and we can identify commonalities in them that are not necessarily linear. So imagine, for example, whoops, we've got something that looks a little like this. So I've got some data here. I've got two variables, I'll call this x and call that z. If I do a scatter plot of this, it looks like that. Now, anyone can visually look at this and say, well, there seems to be some kind of common dimension here, something like that. And in fact, if you can imagine, we could take this, this nonlinear dimension, this is sort of like a piece of string, and we're laying it along the data cloud here, and at each equidistant point, there's like a little hash mark that corresponds to a measurement. So this is like, 0 and 1, 2, 3, 4, and so on, going all through that line. We could extract that component, and then straighten it out, something like that. That's kind of weird. Something like that. Call this new component, I don't know, P. And now what we've done is constructed a new principal component variable that was a nonlinear function of x and z. So in other words, when p is near 0, what we're saying is that x and z come from somewhere in sort of this vicinity. When p is near its maximum, x and z are sort of near this vicinity. And as p changes, from 1, 2, 3, 4, 5, we don't just get a linear interpolation from there to there. We can actually get a nonlinear interpolation moving through x and z. So this can be handy if you believe that x and z are measures of the same concept, but their relationship is not linear for some reason. Now, nonlinear principal components analysis is implemented in R, and I've got an example for you. Here's a nonlinear feature extraction program. It uses the PCA methods package, the same as we used last week. And what I've done is I've created an x and z variable that are nonlinearly related to one another. You can see that they're pretty weird looking, but there's definitely a common dimension. There's x1, z -1 is kind of hanging out with itself here. And then as this dimension changes, we're always going down on x, but we go up on z and then down again. So this latent dimension is sort of monotonically related to x, but non-linearly related to z. And there are all sorts of reasons why this might be the case. For example, there might be some latent dimension of economic health, and economic health is always monotonically associated with growth. More growth is better, less growth is worse. But inflation is different. As we know, high inflation and low inflation can mean very different things in very different contexts with respect to economic health. Low inflation could be symptomatic of bad economic health if the reason for the low inflation is low growth. In other words, if we're on an unfavorable part of the Phillips curve. Oh, I guess the Phillips curve is with unemployment. Whatever. Well, no, that would still be an unfavorable part of the Phillips curve because you'd be at high unemployment. Anyway. Actually, come to think of it, I didn't think about this till just now, but the Phillips curve would be a pretty good example of this because the Phillips curve relates unemployment to inflation. That relationship is a curve. It's nonlinear. And if you believe the Phillips curve was true, there would be this latent underlying dimension that you could extract from those two. I'm not sure what that would be. There would be level curves of the economic growth function. Whatever. Shouldn't talk about economics. Anyway, at least I shouldn't talk about macro. Anyway, okay, so for some reason I want to extract the principal component out of x and z. So I'm going to use the PCA methods library. I'm going to use NLPCA. And while this runs, I'll talk about what it's doing or how we do this. So NLPCA uses the same basic concepts that we just used in neural network package, but it's designed to be auto-associative, whereas the neural network package is not designed for auto-associative networks. In fact, you can get some very, you can have a hard time making it estimated an auto-associative network. I tried for a while, and you can force it sometimes, but it's not pretty. NLPCA has this built in. So I've scaled the x and z variables. NPCS says I want to extract one principal component. And max steps, 1,000 means it's going to perform 1,000 estimates of the backpropagation algorithm. And it actually does not check for convergence. You just give it a number of steps that you wish to have it perform, and it does that. And in fact, I would recommend you specify that number to be pretty high because you won't necessarily know whether it's converged well or not. And I also recommend you maybe repeat this multiple times to ensure that you've extracted the correct components. So now we have an object, pca.nn, which this tells us what we've got out of it. And you can see that the r squared of this principal component is pretty high. It also tells you what kind of neural network it used, a 1-4-2 neural network structure. And I can tell what principal component it extracted by looking at the slot. Let's see, pca.nn slot scores. That's where it's going to store the answers. So I've got 1,000 observations, and for each one of those 1,000, it's told me how far along I am on this imaginary line that I've drawn inside of this data cloud. And you can see what this looks like if you plot x against the scores. So here you can see, just as we forecasted, x is monotonically related to z. Or I'm sorry, take that back. X is monotonically related to the principal component, but z is non-monotonically related to the principal component. For small values, the principal component, and for large values, the principal component, z is negative. For medium values, the principal component, z is large. So in other words, we've gotten this common principal component out of it, and then I can take this principal component and I can use it for something. I can extract a score, call it a common factor, and then use this as a measure of something that I'm compiling. Well, anyway, that's it for this week. Thanks for tuning in, and I'll see you next time.